Hello science students, today we're going to start talking about the wavelength equation. We've taken a look at the different parts of a wave, including the frequency, amplitude, and wavelength, and we've taken a look at different types of waves, so things like electromagnetic waves, transverse waves, longitudinal waves, compression waves, gamma rays, x-rays, light waves, all these different things. So we've taken a look at those things. Now we can start talking about how to do a little bit of math surrounding those things. So your goal today is just to be able to understand the relationship between the parts of the wave equation or the wavelength equation. So we're going to take a look at that. But first, let's talk about there's three things that show up in the wavelength equation. First one is wavelength. The symbol for wavelength is lambda, and the standard unit for that is meters. Wavelength is literally just length. It's a measurement. So if we talk about length, width, and height, those are measurements that are in length. Wavelength is the same thing. It's a measurement that is in length, and therefore its unit is meters, and the symbol we use is this little squiggly looking thing called a lambda. The second thing in the equation is velocity. How fast is the wave going? We've talked about this quite a bit, especially earlier in physics. Velocity symbol is going to be v, and its unit is meters per second. So how far can it go in a given amount of time? Our final part, which has the only brand new unit that we have not seen yet, is frequency. We're going to use the letter F for that. And frequency is how often something shows up in a given amount of time. So it's a per second. It's 10 waves per second, 30 waves per second, 80 waves per second, a million waves per second. Whatever that wavelength is, it's per second. So the units are 1/seconds. We have another name for that though, and it's called hertz. And the symbol for that is Hz. Let's take a look at the equation itself. The equation itself is that the wavelength of a wave is equal to the velocity or the speed of that wave divided by its frequency. And you'll notice that that works out nicely. This is meters per second. We divide by per seconds, and we're left with a length of just meters. The triangle form of that looks like this. So velocity divided by wavelength is equal to frequency. Wavelength times frequency is equal to velocity. And as in our equation up here, velocity divided by frequency is equal to wavelength. Let's talk about the relationships between those variables. Wavelength is proportional to velocity. So if frequency remains constant, which is how many waves are coming past, and we increase the velocity, the wavelength has to be longer. Otherwise, the frequency would have to go up. The reverse is also true. If the frequency stays the same and the velocity decreases, the wavelength also must decrease. Otherwise, the frequency would increase as well. The velocity is proportional to the frequency. So this also kind of makes sense. So if I have a wave and it starts to move faster, more wave fronts or more wavelengths will get by per second, and therefore the frequency must increase. The same would be true if we decrease the speed. So if we're going slower, fewer waves would go by, and therefore the frequency would decrease. Finally, wavelength is proportional to 1 over the frequency. So they are what's known as inversely proportional. So as the frequency increases, the wavelength actually decreases, and vice versa. Okay, so just to demonstrate that very quickly, so if I have a very high frequency or a very low frequency, if I have a high frequency, my wavelength is very short. So I'm seeing a lot of waves, but they're not very big. If I have a long wavelength, I have a lower frequency. Fewer waves are coming past in a given amount of time. Okay, just a quick video to introduce the wavelength equation. Please watch the next video for some examples on how to use that equation and do some calculations.